Hi everybody, welcome back to Chem 140. Sorry about that, I had some setup I was getting done here. Alright, let me push that. There we go. So, alright, we left on this slide yesterday. I didn't give you all a chance to bounce these equations. I have a bunch of these for you to do, and what I'm going to do is I'm going to give you like 5 or 6 minutes to do as many of them as you can. I'll put all the answers on the screen, and then if you have any questions about them, you can ask me about these again at some other time. But I don't want to spend too much time on this. I do want to give you the opportunity to work on it, though, if you so choose. So go ahead and balance these equations, and in about 5 or 6 minutes, I will check up with you. Once you've got the equation, try and type it as best you can into the chat. All right, let's do 1 or 2 more minutes and we'll go over the answers. All right, I'm just going to put the answers in here. That does require me to get the pen tool. There we go. So let me see here. So this is a 3, and this is a 2, and this is a 4. And then 2, 2. Now you might be asking, how the heck am I doing these so quickly? And I'm basically doing the whole fate thing. So I noticed that, like, okay, what I'm trying to do is I'm trying to pick the most complicated thing. So for example, in this iron one, right here, I know that all the oxygen is going to end up in the same spot. So these numbers multiplied together have to equal these numbers multiplied together. So I immediately can solve the complex ones and then just leave the simpler ones to fill in. Now, I'll go over any of these if you'd like me to, but I'm just going to fill in the answers for now. So let's see here. So this is going to be 2. This is 3, and then this is 6. So there's that. 1, 2, 2. 3, 5, 6 is 3. 4, 7, 6, 3. There we go. And then that. And then there. There should be a 12 in that space. I just can't fit it in there. Okay. So there's all the answers, just so you can have them on the screen. And if you want me to go over any of them, like, let me know in the next minute or so. Otherwise, you can always just ask me in the Discord if you're trying to do that for yourself and you're like, I can't seem to get this answer. Let me know and I can walk you through that too. Number 6. Okay, I got to figure out which one number 6 is. This one, right? Let me know if that's not the right one. So let's put this on the screen. The polyatomic ion would be 4, I think. I could fit them both on the screen. I don't know why I don't have PowerPoint appearing. Probably because I just hadn't opened it yet since I prepared the stream here. Okay, so let's write down that equation. So I got CH3. So I got ethanol. This is the oxidation of ethanol. CO2 and H2. All right, so just like we always do. 2, 6, 2, I think that's right. And then all right, so we'll got something like this. So I'm going to do carbon first, because I try to go down the list here. So carbon has to end up here, so this has to be true. And then I end up with, so 5. And then hydrogen, I have 6 of them. They have to end up here, so this has to be true, right? So that means I have 6 hydrogen, and then I have 4 plus 3 oxygen, which is 7. So I can't make this number be 7, right? I could do 7 halves, but it turns out I don't have to because I already have 1 here. So this right here just has to be 6 of my oxygen. And if I do this, it is. So then I get 3 times 2 is 6, plus this one is 7, and the equation is balanced. So there's the first one, or the 6th one, I guess. And then somebody else wanted to see the sodium phosphate and magnesium chloride, I believe. Oops, oh, I cleared all the colors. No. Let me get my purple back here. Alright, so I got sodium phosphate. And I've got magnesium chloride. Makes magnesium phosphate and sodium chloride. Now you're going to notice that I'm putting my phosphate just as phosphate, just to simplify, because the phosphates stick together. They're polyatomic ions. They very rarely react. It's not universally true, but almost all of the time they remain as polyatomic ions. So you just write them as is. So then I have 3, 1 of those, 1 of these, and 2 of those. 1, 2, 3, 1. I believe that's right. Alright, everything is a mess and it's terrible. But let's start with the most complex thing. So that's Mg3PO42. So I'm going to put a 3 here and a 2 here. Because that will give me 3 magnesium. And it also gives me 6 chloride. And then up here, I would have 2 phosphate, but also 6 sodium. And now I just need 6 of each of these guys, so I just do this and it's all done. So starting with the most complex thing and then seeing what leads to that is a great strategy. That's how I do this. I do them in like 10 seconds anyway. Now you're learning, so you're going to take more time than that. That's totally fine. You just don't want to take 20 minutes to balance one equation. That's too much time. All right. Any more questions, let me know. We'll put this back on the screen here. Otherwise, we're going to go on to Unit 15, which is very nearly the end of the textbook. All right. I scrolled it a little bit too early there, so... No, I don't want to keep the ink on my screen. Don't be ridiculous. All right, Unit 15. There we go. So there are only 2 units left. Here is one of them. So kind of the whole point of taking Chem 140 is to take these 2 units, 15 and 16. The stoichiometry unit is basically the whole reason we have this class, because we found that when people got to Chem 161 without Chem 140, that a large subset of them had trouble doing stoichiometry, because it's dimensional analysis from the Black Lagoon, basically. It's really, really complex and difficult if you were just leaping in blind. But now that we've had 14 units of stuff to prepare for this, it's going to be very straightforward. In Unit 12, we explored concepts like, remember P2O5? We did P2O5 to death. And we said that in 1 mole P2O5, there were 5 moles of, say, oxygen. And that came from this number right here. Now what we're going to do is, instead of looking within a molecule, we're going to look within a reaction. On the screen, I have a reaction. And what I can say is that I can say, if I put in 4 moles of this thing, I will get out 6 moles of this thing, right? So if this goes into the container, I will get this many moles of water out. I also get NO, but if I'm only interested in these two things, then I'll just choose those to relate. And I can relate any two things that I choose to for this given reaction. Because every time I do a cycle being what you see in the reaction, I would consume 4NH3 and 5O2, and I would produce 4 NOs and 6 H2Os. And I can pick any two of those per cycle and write a relationship by that, and then multiply it by a mole to get this mole equation that we have down here. All right. Likewise, if I react 4 molecules of ammonia, I can get 4 moles of nitrogen monoxide out. And I could write that statement, which I would then multiply by a mole. And this is just going to generate all sorts of different statements. This is every possible combination of 2 that I can generate here. So 4 choose 2 is these 6 possibilities. Now, for this reaction as written, these are all valid for this reaction. If I had a different reaction, all my statements change. So these are not going to be universally true statements. 4 moles of ammonia is not always going to equal 6 moles of water. But for this specific reaction, it is true. And so if you can make these relationships, you can now do conversions between them. So for instance, if I have 16 moles of ammonia, and I want to put in there abundant oxygen, that is, all the oxygen that I need to react with 16 moles of oxygen, how many moles of water would you make? Well, you do the same type of stoichiometry, or that's the next word we're going to talk. You do the same type of dimensional analysis that we would normally do. Cancel out the units. And then, what numbers go in these blanks right here? Well, they come from the balanced chemical equation. So for every 4 moles of ammonia I use, I create 6 moles of water. And so this would be 16 times 6 over 4, which I believe is 24. Because 16 divided by 4 is 4, and then times 6 is 24. There we go. All right, I'm going to hit erase. Now I want you to do it. I'm going to use 25 moles of ammonia. If I want enough oxygen to react with that, how much oxygen do I need? How much oxygen would react with 25 moles of ammonia? Do the calculation. Type your answer in the chat. All right, one more minute. We'll go over the answers here. All right, let's go over the solution here. I don't think I have enough space on this page to do this, so I'm going to just go back over here and clear, and we'll write it out. So I got 25 moles of ammonia, and I want to find out how many moles of O2 react with it. So I'll set up my units to cancel out what I don't want and replace it with what I do want. And then we'll look at the relationship there, which I can't see because I don't have the equation. So it's... I mean, I guess I could just do this now. So for every 4 moles of ammonia I put in, I also have to put in 5 moles of oxygen. And so that's 125 divided by 4, whatever that is. That's 125 times 4, Wes. What's wrong with you? And I get 31.3 moles of oxygen. Only 3 sig figs because that's how many I had with my initial number. All right. So this is a pretty straightforward concept. We can convert moles of something to moles of something else. Guess what we're going to do with it? I wonder. Maybe we won't use moles? Maybe we'll use something else. So here we go. This is just a concept check. Hey, guess what? I don't balance your equations for you all the time anymore now. So what you need to do is first balance my equation. This is the combustion of glucose. This is what your body does to consume sugar. It reacts with oxygen and you produce CO2, which you exhale, and H2O, which your body just uses in other places because you need water all over the place. So first balance the equation, make sure you do it correctly. And then if I have 24 moles of glucose and all the oxygen I need to burn it, how many moles of CO2 would you make? And then if you do a reaction that produces 180 moles of water, how many moles of oxygen were used? All right. So do those 3 problems, again, 5 or 6 minutes or so. We'll go over the results when we get back. Let's do 2 more minutes and then we'll go over the answers. I misclicked on the thing. Let's go over the answer here. So first I gotta erase that, and then I gotta click over here. All right, so first let's balance the equation. Now, if you need me to do this for you, I will. It will require me to copy it back down here. So I'm just gonna fill in the numbers. So they're all 6s except for this first one, which is a 1. And then I need to click down here. There we go. Okay. So let's see here. I have 24 moles of glucose. And I want to know how many moles of CO2 would I make? So we'll go moles of glucose, moles of CO2. And we just fill in the numbers. So for every 1 mole of glucose I make, I use up, I also make 6 moles CO2. So whatever 24 times 6 is, which I believe is 144. Not minus 6 times 6. Yeah. 144. And then if I do the reaction and make 180 moles of water, how many moles of O2 were used? So we could go moles H2O, moles of oxygen. And all the numbers were 6 before, right? So I just do this. Well, those numbers just cancel each other out too. And there you go. Because that checks out, right? If I make the same amount of H2O that I put in for O2, because it's 6 versus 6, then if I put 180 in, I should also get 180, right? All right. Yeah, this is just O2 because it's asking you for moles of oxygen, O2, not moles of all the oxygens in the molecule. We take the inventory to balance the equation, and once we've balanced the equation, we don't need the inventory anymore. Then it's just which specific species are we being asked to look at. All right, let's go do something obvious thing with this, right? Like, okay, we don't work in moles, let's work in grams. Now, this is just going to be a little demonstration here that if I take these numbers and I turn them into moles, I would get this equation here. So 4 moles times 17.02 grams per mole. So this one is ammonia. This one's oxygen. This one's nitrogen monoxide. And this one's water. And what ends up happening is if I convert these masses to grams, I get this. Which isn't exactly right, but to 4 sig figs it sure is. So 228 point whatever goes in the tenths place. So that just shows us that the conservation of mass is indeed conserved with these calculations. So when we do these conversions from moles to grams, you can be assured that you aren't going to lose matter or get a weird result. It's all baked into how these equations function. So let's do that. Let's actually turn stuff into masses and do these calculations. All right. So the process of doing this is called stoichiometry. And again, this is the kind of the whole point of why you're here. If you can make it here, you can make it anywhere in Chem 140, which, I mean, that checks out because we're at the very end of the quarter, right? Hopefully you can make it here having made it thus far, is what I mean. So. All right, so you know how to turn anything from grams to moles or moles to grams. You also know how to turn stuff from particles to moles and moles to particles. So I can ask you any question I really want to. And so that's what we're going to do. So remember this chart? Yeah, it's back because we're doing the same thing, right? We're just going to use balanced equations. Here's our balanced equations for sodium azide. The decomposition of sodium azide is very important industrially. Or not industrially, sorry, commercially. Because the product of the decomposition of sodium azide is nitrogen. This is particularly useful if you need to make a lot of nitrogen extremely fast, such as, say, in your automobile airbag. And the way that this works, we'll go over here and draw a picture. The way that this reaction works is that in your car, so let's draw my Jeep Wrangler here. So my Jeep Wrangler is basically a box, right? There's my Jeep Wrangler, and there's the wheels. All right. There's a steering wheel right here, and the steering wheel has a steering column, which has a tube that leads to a container. This is a little exaggerated, obviously. And that container is connected to a circuit which connects to the bumper. Inside is sodium azide. Now, if something collides with your bumper firmly enough, the circuit activates and ignites the sodium azide, which then decomposes into sodium and nitrogen. And it'd be something like this. So you'd make a bunch of nitrogen really quickly. And so this reaction goes extremely fast. It fills this container, and it fills going up the steering column, and then it keeps expanding because it hits the path of least resistance, which is the panel over your steering wheel where the airbag is deployed, and goes foomp. Oops, I tried to foomp. There we go. Foomp, and it fills up way before you strike your face into the steering wheel. Because if you're going really fast, you have a lot of momentum, and you will continue to sail forward even when your vehicle doesn't. And so the airbag can save you. This is a major invention in I want to say it's the 80s is when this technology started to come out. So this reaction is particularly useful for that. All right. And so the question I have for this, I'm going to just let you try this, is if you decompose 20 grams of sodium azide, what mass of nitrogen do you make? Go ahead and try and do this, because you already know how. Because you could convert moles of sodium azide to moles of nitrogen, right? So you just have to do the first step and the last step, which is turn grams into moles and then turn your moles back into grams. So give it a shot. We'll go over the answer in about 4 or 5 minutes. And then we'll take our break because we're due for one. All right, one more minute. We'll go over the answer here. All right, let's go over the answer here. All right, we don't need this vehicle anymore. Oops, I do want to have the brush tool selected, though. Oh no! I dropped the pen on the floor. That's okay, the cat will pick it up. All right, so we know that if I have something in grams, I can turn it into moles. And since the problem wants us to go from sodium azide to nitrogen, we could turn moles of sodium azide into moles of nitrogen, and then turn that into a mass. So let's do that. So I got grams of sodium azide. We'll turn that into moles of sodium azide. How many grams of sodium azide are there in a mole? Well, that's what Lentech is for. Hopefully you've bookmarked Lentech by now. Otherwise, you're going to have to calculate manually. There we go. That would be the number of moles. And then we also know that the number of moles of NaN3 can be converted into moles of N2. And then I just make the relationship for the balanced chemical equation, which I've shown above. So for every 2 sodium azide I put in, I get out 3 nitrogen. Now, these numbers only show up in this expression. Don't start putting 2s and 3s everywhere. So this relationship has to still be true. In 1 mole, it weighs this much. Don't suddenly put a 2 there. Okay? So the only time the coefficients appear is in this relationship when you go from moles to moles. And then finally, we'll go from moles of N2 to grams of N2. And I want to write in a true relationship for this too. So in 1 mole, how much is that? Well, Lentech will tell you. You just type in N2, N2, 28.01. The last thing you want to do is punch it all in the calculator, and you want to make sure you do it correctly. Use parentheses. Put parentheses around everything on top, and then put parentheses around everything on bottom. I believe the answer is 12.9. Yeah, it is. There you go. That's how we do stoichiometry. All right. So there was our problem completed. We're going to go take a break because I need to refill my water. So I'm going to put this on the screen with the music going again. And I'll see you in just a bit if I can find the track I was going to play. There it is. Alright, welcome back. We'll put the next problem on the screen. Alright, for this next problem, we're going to do the same thing. It's the same reaction, but this is a micro experiment. We're going to use like micrograms of sodium azide. How many molecules do you create in this micro experiment? Since you probably don't have the reaction memorized, I'm going to rewrite it on the board here. So 2 NaN3 makes 2 sodium and 3 nitrogen. All right, so go ahead and try this problem. You're starting with a mass, but remember this time I want you to tell me how many particles are generated. So go ahead and try this, and we'll go over the answer in just a second. 5 minutes or so. All right, 1 more minute, we'll go over the answer. All right, let's go over this together. All right, so for this micro experiment, we're going to use a very small amount of sodium azide. We're going to follow the same process that we did before. We're going to start with grams of sodium azide, which we're going to turn into moles. And then since we're asking about N2 again, we'll just turn that into moles of N2. And then instead of grams this time, we'll turn it into particles of N2. So most of this is actually going to be the same as it was in the previous problem. Yeah, that's what I want to do. Never mind. So we'll cancel those out. Although what I don't like is where I wrote this. Boop. So we'll just put it over there. And in a mole of sodium azide, well, we already did this before. It's 65.01 grams, so there we go. And then just like before, we'll turn moles of NaN3 into moles of N2. And according to the balanced chemical equation, which should be up there in red at the top of the screen here, so for every 2 moles of sodium azide I put in, I get 3 moles of nitrogen out. And then we'll turn this into molecules. Well, how many molecules are in a mole of anything? It's your favorite number, Avogadro. There we go. And so all of it goes in the calculator. Again, be very careful with parentheses here. Especially when using exponents. I got 2.53 times 10 to the 16 is what I got. I was holding down a button. It didn't actually work. All right. In the interest of time, since people seem to be doing fine on these problems, I'm going to skip the next few and just go straight to the now you try it. Because we probably don't need to do 6 of them. But the answers are available for these. Oh, the balanced equation was on the screen there. So you can try these problems on your own. These involve the production of ammonia from hydrogen and nitrogen, so you have to write an equation for that, but that's okay. I'm going to let you try those on your own, but I'll have you do these right now. So, pyrite is a common iron ore that is found in the earth. And if you burn it in the presence of oxygen, you make SO2 and rust, or iron 3 oxide. So, what I want you to do is first balance the equation. And then if I combust 38.8 grams of iron 4 sulfide with oxygen, how many grams of sulfur do I make? Or not sulfur, I'm sorry. Sulfur dioxide do I make? And then how many molecules, specifically formula units, of Fe2O3 are produced from that same quantity? So go ahead and try these 3 problems. Balance the equation, do these 2 conversions. 5 or 6 minutes, and we'll go over the answers in just a bit. Let's do 2 more minutes and we'll go over the answers. All right, let's go over the result here. Over here. So first I got to balance the equation real quick. So let me finish getting this all set up here. And then I will do that really fast. So let's see here. So let's do, so we'll say this and that. And I would need 11 over 2 to make this work, I believe. 4 sulfur, so 4, 8, 11. Yeah, that would work. Okay, so then this would become, so 11, so this would be 4, this is 11, this is 2, and this is 8. So that should be right. And we'll check your math. We'll see what we can do here. All right, so for the first problem, we can get rid of that. So we've balanced the equation. How many grams of SO2 are produced from 38.8 grams FeS2? So we can turn this from grams into moles, and in a mole, according to Lentech, there are FeS2. 119.98 grams of FeS2. Now, without seeing your numbers, Chris, I can't tell where your math error is, so try and follow along carefully with what I've got here. See if you can. It could be as simple as just typing something in the calculator wrong. So we want SO2, so I'm going to do this. And then, let's see here. So I put 4 moles of FeS2 in, and I get 8 moles of SO2 out. That's not what I meant to write. And then I'm going to turn moles of not FeS2. That's what happens when you don't get enough sleep, you guys. Moles of SO2 to grams of SO2. And I want to say this is like 64 or something. SO2. 64.06. Alright. That I just have to type in the calculator. 38.8 times 8 times 64.06 divided by 119.98 times 4. I got 41.4. Yeah, it looks like everything that you did was correct, because I got the same answer. What am I doing? Grams SO2. There we go. Now, how can you get more of that than you started with? Well, it's easy. You're also adding oxygen, right? So, the sulfur that you had in the iron sulfide is a small fraction of the FeS2 that you started with, but the oxygen that you're combining basically doubles its mass. So, whatever half of 41.4 is probably the mass of sulfur that you used. All right. How many molecules of Fe2O3 are in this? Now, because we're doing all of this stuff, again, none of this has changed, so we'll just copy and paste it. And then for every 4 moles of FeS2 I put in, I get 2 moles of Fe2O3 out. And we'll just write formula units, or funits. Because it's ionic, right? So we want to have formula units. And how many formula units are in a mole? Well, it's Avogadro's number again. If you're counting something, it's always Avogadro. And so I got, for this one, 9.74 times 10 to the 22 funits. There you go. 38.8 times 2 times Avogadro divided by 9. Okay, yeah. I feel pretty confident that I did that right. All right, so that's how we do stoichiometry. I think that the major issue that people are going to run into is entering numbers in their calculator, and then also making sure that the relationships you're putting in are valid. So remember that when you're putting in molar masses, it's always 1 mole equals how many grams, and you get that from Lentech. So this is Lentech. This right here is from the balanced equation. And then whenever you do something with a mole to a number, you just use Avogadro. So make sure that you are creating valid and factually accurate conversions, and you'll be in good shape. All right. I don't know if we're going to finish this section today. We certainly won't get through reaction yield. We can do that on... we'll do it on Monday, probably. I don't think that we need to have an extra lecture tomorrow because we're doing pretty good. And we have Wednesday as a review next week anyway, so if we had to use part of that to finish chapter 16, that's fine. All right. Now, in the stoichiometry problems I've been giving you, we have been making assumptions. And the assumptions are that whatever reactant I am using for the given amount that I give you, the other one is provided in abundance. I.e., so if I go back to this reaction that we just had on the screen here, if I'm looking at FES2, I'm assuming there's enough oxygen to completely react with it. In reality, that may not be the case. You may run out of one substance before the other. So, for example, let's look at this cheeseburger formula. So, this is the chemical formula for cheeseburger. If I combine 2 patties, 1 bun, and 1 cheese, the product is a cheeseburger. Oh, okay, good. Oh, I'm glad you found it. Yeah. It's super easy to do that sort of thing, so don't get discouraged. All right, so there's our formula for cheeseburger. Let's suppose I gave you this set of ingredients: 10 patties, 6 buns, and 8 slices of cheese. How many cheeseburgers could you make in total? Well, that's relatively easy to do the calculation for, but we have to do it multiple times, and here's how we do it. So if I have 10 patties and 2 patties per burger, 10 patties would make 5 burgers, right? But with 6 buns, where you use 1 bun per burger, you could make 6 burgers, right? And then with 8 slices of cheese, where 1 slice of cheese is used per burger, you could get 8 burgers. So how many burgers do you actually make? Well, a burger requires all of the things, and when you run out, you stop making burgers, right? So after I make 5 burgers with my 10 patties, I'm out of hamburger meat. All I have are buns and cheese. Those are not cheeseburgers at that point. That's just strange, I guess we'll call it. So whichever number you get the least of, right? I mean, if you're going to make a burger, you put 2 patties, right? We're hungry. We're college faculty / students. We're basically starving, right? We have no money or funds, and all of our energy goes to brain power. So we need as many burgers as we can get. Unfortunately, once you run out of meat, you can't make further burgers. So the number of burgers that would be produced would be 5. Because the 6th attempt, there is no money. Not money, I'm sorry, there's no meat. Still hung up on the money part, I guess, right? So this is the concept of the limiting reactant. The limiting reactant is the substance that you of your starting materials that you run out of first, and it will govern how much product you can produce. Now, the way to determine, the correct amount of products to make is to just do the problem for all of the reactants that you have. And when you get to the end of the problem, whichever result is smaller, that's the answer. That's how much is made. So in this case, I would have made 5 burgers and I would just ignore these other results because I can't make 6 or 8 burgers. I run out of other stuff. So that's the concept behind the limiting reactant. So for our purposes, we're going to do calculations exactly like we did before. But because we now have a limiting reactant, because multiple reactants are given, and it's not assumed anymore that one is in excess, we just have to do the problem twice. Another way to look at this is to convert my reaction into just amounts. And so if I react 4 grams of hydrogen, I also need at least 32 grams of oxygen. If I put more oxygen in there, it's left over. So for every reaction, if you don't have the correct amount, then you run out of one thing, and the other thing is in excess. And the excess thing doesn't affect your calculation. It's just not the number that you need. You cross it out. And you're going to see that in a second here. So our job in these problems is to figure out which is the limiting reactant. It is not the one that you have less of to start. It is the one that produces less product, okay? So even though I only put in 4 grams of hydrogen here and it was the limiting reactant, it is not because I only had 4 grams. If I had 8 grams of hydrogen, I'd actually run out of oxygen first, believe it or not. So resist the temptation to just guess one and guess the smaller one, because you really are just, it's a crapshoot at that point, 50-50. So now to solve limiting reactant problems, here's the most efficient way to do this on the board. But what I'm going to do instead is to just say convert both reactants to the desired product. And then you can just skip step 2 because you've already done step 2 and doing step 1. So if you want to, you can just stop at moles of the product and then whichever one is less, turn it into grams and you're all set. But honestly, this way works easier for beginning students. And so that's what I'm going to do. I just haven't updated this slide and I apologize for that. So we're going to just convert both of the reactants all the way through to the product. And we'll do that in grams. And then whichever one of those makes less product in grams, that's the limiting reactant, and that solves the problem. Circle that number and cross out the other one. So we're going to do an example here. We're going to burn 40 grams of methanol with 46 grams of oxygen. Now, the way that you know you're doing a limiting reactant problem is that I give you multiple reactants. Most problems I will just say, I'm going to combine, or I'm going to react these things together. If I use X amount of this, what do I get? And then it's assumed that it's excess. But here we don't assume it's excess anymore, because I have given you all the reactants. This is all you get, 40 grams of methanol and 46 grams of O2. So what we're going to do is we're going to do the following. We're going to take the mass of our reactant, whatever it is, and we'll turn it into moles. And then the problem is asking us for mass of CO2. So we'll go moles CO2, mass CO2. And that'll get us to the end. And then whichever one of these answers is going to be less, that's the result. That was the limiting reactant. Okay, so here we go. So we're going to take 40 grams of methanol and 46 grams of O2. All right, so we'll turn grams into moles. Head straight back to Lentech there. So let's see here. Methanol. Oops, I was typing in methanol. That's not going to work. It's in the automatic thing. It knows what methanol is. I could have just picked it from a list, but... Alright. So methanol is 32.04 grams per mole. Then we'll turn moles of methanol into moles of carbon dioxide. And according to our balanced chemical equation, which I scrolled off my screen here, for every... Oh, I gotta cancel this first. For every 2 methanol I put in, I get 2 CO2 out. And then I just convert from moles to grams. 1 mole is 44.01. That one I have memorized. All right, so if I had 40 grams of methanol, the maximum amount of CO2 I could potentially produce with that is, these are both 2, so I'm just going to cancel them. 54.9 grams CO2. Okay, fair enough. Now let's do the same thing with oxygen. What's the maximum I could produce with this mass of oxygen? Well, 1 mole of oxygen is 32 grams. Now for this one, for every 3 moles of oxygen I put in there, I get 2 moles of CO2 out. And then I do the same thing over here that I did before. And then I just run the numbers. 46 times 2 times 44.01 over parentheses 32.00 times 3. All right. So now that you've seen both results carried all the way through, which one will be the limiting reactant? Well, it's the one that produces less. So LR, limiting reactant. This is the limiting reactant. The limiting reactant is oxygen. What does that mean, this one? That means that this one is in excess. Or I just write the letters XS, right? Here's what we do with that calculation and its answer. We go, you just scribble it out. Now, don't obliterate it. Like, don't scratch through the entire problem so badly that you can't read what you wrote. Because what if you need that number later for some other application? Who knows? So, never obliterate things. Just draw a scribble through it and ignore that problem part because it doesn't apply. It's not the limiting reactant. This is how much we could produce if we ran out of methanol first. But we don't run out of methanol first. We run out of oxygen because it produces less product. All right, so that's the gist of how we do a limiting reactant problem. And my slide here just kind of walks you through that. Now, this is doing where you just convert to moles of CO2. So converting from moles of CO2 to grams of CO2 is just an extra step. But because it makes it easier for students to follow, I feel like this method is just easier to teach. And I need to go and actually fix my slides. But I think this is also consistent with the workbook for what it's worth. So you can do it either way. It's up to you. All right. I'm going to have you try this one problem before we call it a day because we're almost out of time. I'm going to give you PF3 and F2, 100 grams PF3, 50 grams of F2. Which one's the limiting reactant and what mass of PF5 do you actually make when you mix these quantities together? I'll give you 5 minutes or so to do it. Then I'll do the answer. And then we're out of time. So see you in just a bit. All right, we're almost out of time, so I'm going to just do this problem here so that we have it done on the stream. All right, so same deal as we did with the previous problem. We're going to take, we're going to take grams of our reactant, turn it into moles. Then we'll turn it into moles of the product that we want, which is, well, there's only one product, so we'll just do PF5. And then turn that into a mass. And you'll be all set. So let's try this out. So I have 100 grams PF3, and I have 50 grams of F2. All right. How many grams are in a... Oops, that was a little too close to that. How many grams are in a mole of PF3? I don't know. 87.97. Yeah, that checks out. All right, and then we'll turn that into moles of PF3 becomes moles of PF5. And this is just 1-to-1 because you're just combining the two. And then moles PF5, grams PF5. Okay, how many grams of PF5 are in a mole? We'll just go boop. There we go. 125.97 is what I got there. And so we'll punch all that in the calculator. And for this, I got total 143.2. So there's our result for the first one. And we can do the same thing with the second one. So I don't know what F2 is. F2 is what, 38? Well, Lentech will tell me. 38.00. Yep. And so, again, 1-to-1 there. And it's the same mass of PF5 per mole. So in this case, we get 50 times 125.97 over 38, and I get 165.75. Well, it should be 165.8, I guess. PF5. All right, which one is the limiting reactant? It's the one that there's less of. That's this one. So the limiting reactant was PF3. This one's in excess, and we scribble it out. Nobody needs it. Oh no, we lost the one? Yeah, that's no good. But hey, that means that you're like 90% of the way there. Just make sure you don't make that mistake on Canvas, because Canvas will be like, oh, it's wrong, sorry. And you won't get points for it, and that's no good. Alright. So that's how we do those types of problems. We are out of time. We'll do another one of these next week on Monday, and then we'll do percent yield, and we'll finish off chapter 15, and we'll move on to unit 16. What's my quiz? So there's a quiz on unit 13 and 14. I put that up online yesterday. And so it's due a week from yesterday, which I believe is the 7th. I ran out of space to put that at below because it would scroll off the screen. I only have 2 lines worth of text. But that announcement should have gone out. So that assignment will be due next week. You have other assignments that are due this week. So lab worksheet number 4 is due tonight. Quiz number 7 is due tomorrow. So you have some work to keep you busy. But do some practice on Unit 15 here, because next week when we do Unit 16, we're going to do a little bit of new stuff. And then a lot of this too. So it'll just be that. And that'll be how we finish off the class next week. So no extra lecture tomorrow, just for my other class. So if you see a video go online, it's for 121. You guys, there won't be a 140 video on Wednesday because we don't really need it. So I guess that's all I'll see of you guys until next week. Make sure you get those assignments in that are upcoming. Let me know if you have any questions. Have a wonderful weekend. Take care.